maze, but you can step only one direction all the time, so it's not as big, really big.
Good morning, everybody. Welcome to Advent of Code Day 23. I'm Thomas, and my guest today is Frank. Good morning, Frank.
Hello, Thomas. Nice to be here.
Yeah, you're welcome. Frank, can you explain us the puzzle for today? It looks like a maze. What is it?
Yeah, a long walk it's called. So we are presented with a maze, and this time we do not have to find the shortest path, but instead the longest path. And here definite a start position is in the left upper corner. There's one tile missing with a dot, and in the lower right corner there's the end of the path. And now we want to find through this maze the longest possible path. And there's one rule here. These arrow tiles have the meaning that you can go only in the direction of the arrow. So there are arrows in all four directions. In the real puzzle here, it's only two directions. But it's basically as simple as that. So you start at the start position, and then you search the longest path. Now, for shortest path problems, we have Dijkstra and other possibilities to go. But for the longest path, it turns out there is no algorithm. It's an incomplete, and the only solution is to try out all possible paths and then take the longest of all. And it turns out for the first start, this puzzle is made in a way that there are not that much paths. So it's actually that simple. Implement most likely a depth first search, where you iterate all paths, and then you will find one of them which is the longest, and that's the solution.
Okay, so the hardest challenge is to find the longest way, not the shortest way. Okay,
yeah, well, we need to implement it. I implemented it again with a queue, and then always pop from the back of the queue to make this a DFS. Also, in the queue, I push as a state all visited positions I found so far, which makes it a little bit memory intense and clumsy to implement a bit. But then it runs, and here is the handling for these arrows, which looks not too nice, but well, we have to implement it here. But then it simply runs here. So just take the length of the path. So in the second star, we are presented with a situation that these arrows are all gone away. They are all normal dots in this maze. So the effect.
You got more possibilities to find the longest way now.
Yeah, now these arrows actually in the first part, they block some paths, because if you go in one direction, so here you have only the possibility to go in one direction. Now if you find an arrow which goes in the other direction, then this path is blocked, which minimizes the number of possible paths. So now the arrows are gone, and we are presented with much more paths. And if we try to run the DFS in the way I implemented it, it would run for hours. It's simply too much paths. So we have to optimize this somehow. And actually, after reading solutions in the solution thread, there are some users which use the same algorithm from the first thing for the second star, and it works in 2 or 3 minutes if it's really good implemented. Some did it in Kotlin, some in Rust or C++, and that worked. They reported, they let it run from the first star, the solution for the second star, and then thought about a better solution, and were surprised that before they came up with a better idea, the result came out. But I was not that lucky. My optimizations were not that good, so I had to think about a better solution. And then the better solution is that we optimize this graph. So if we start here, then it needs like 100 steps or so before we come to a position where actually 2 paths are possible. And then we can create from this big maze a pretty small graph with only 30 or so nodes in it, where you can go from one node to the other, and there's always a path length like 100 or 50 steps. And then we can do the same again. Check all paths in this smaller graph, and this runs pretty fast, than 10 seconds in my implementation. So to do this, to optimize this the smaller graph, or to find a smaller graph, we have to implement some helper methods here. I call them find agent, which means if we run from one position in the maze and then find all the crossings that are directly reachable, this is agents here, and then we can optimize it using this function, and then basically do the same again like in the first star. And then the result comes out.
Yeah, nice. Frank, what was the hardest thing this time? The hardest challenge?
To understand how this maze works, because it's so big and the longest path, there's no algorithm. So in the first place, it looks like it's unsolvable. And then you look the maze and you see, oh, it's big maze, but you can step only one direction all the time, so it's not as big, really big. So then after some times I came up with ideas how I can implement it.
Yeah, nice. And big thank you. Some last words for this puzzle?
Yeah, tomorrow and day after tomorrow will be the last days, so we are near the end. I'm pretty happy with it.
Yeah, fine. Then stay healthy. Merry Christmas for you tomorrow, and we see us tomorrow.
Merry Christmas. See you tomorrow.